Hello, so today we are going to do Leetcode Game of Life problem, part of April 12th, I think, challenge. And so the problem says that we have a game of life, cellular automaton divided by, okay, whatever, that's not important. But we have a board, it's made up of M by N grid of cells, such that we have M by N, where each cell has an initial state, which is live represented by 1 or dead represented by 0, and each cell interacts with its 8 neighbors. Okay, let's see, let's try to do this here, let's try to take notes here. So we have 1, which is live, and then 0, dead. And the board is M by N grid of cells, which are where each cell has an initial state. Okay, each cell interacts with the neighbors, horizontal, vertical, and diagonal. Okay, so it's just using the following rules. Any live cell with fewer than 2 live neighbors dies as if it's caused by underpopulation. Okay. Any live cell with 2 or 3 live neighbors lives on to the next generation, and any live cell with more than 3 live neighbors dies. Okay, and any dead cell with exactly 3 live neighbors becomes a live cell. Okay, interesting. So we apply these rules, and we get to the next state. Is created by applying the above rules simultaneously to every cell in the current state, where births and deaths occur simultaneously. Given the current state of the M by N board, we want to return the next state. Okay. So this just seems like a simulation implementation. Maybe we can use some sort of BFS or DFS, but let's see if we can. So with fewer than, so if neighbors, so if count neighbors, if neighbor is equal to 1, which is live, so any live cell with fewer than 2 live neighbors, less than 2, so basically if this is less than 2, we want to basically cell equal to 0. It dies, right? So dies. So this is rule 1. For 2, basically is any live cell with 2 or 3, so where neighbors, if neighbor is equal to, so here with fewer than 2 live neighbors dies. Here with 2 or 3 lives on to the next generation, so bigger or equal to 2. Since we know that each cell, so each cell has, it can have only this neighbor, so let's consider that cell, or the neighbor above it, or below it, or the one in each diagonal. So let's just simplify this for us in 2 to 3 range. So if it's in that range, then okay, let's actually just do this. 3, and this is 2. So if the count is between 2 and 3, then the cell is equal to 1. The next step is any live cell with more than 3. So if cell, so here if cell equal to 1, and now if cell is equal to 1 and more than 3 live neighbors, so the count of neighbors is bigger or equal to 3, then the cell dies. for the last rule is that if any dead cell, so if cell equal to 0 and the count of the live neighbors, again with exactly 3 live neighbors, becomes a live cell. So these are kind of the rules, and what happens is that we want to apply these rules to every cell in the current state and return the next state. So we want to apply these and return the next state. And we want to apply this simultaneously. What does that mean? Yeah, one problem I'm thinking of is if we change a cell and then we go to its neighbor and we change the value of the neighbor, do we need to go back to that cell? Normally, no. And so the thing here is, should we use DFS style or BFS? Or just go through every cell randomly? Yeah, I think we shouldn't do any DFS or BFS here. I think since simultaneously it says we should use the previous board, the board to the original board each time to get the count of live neighbors, since everything happens simultaneously. So what I think here is that we can just use maybe current, and we modify the board itself. And now we can go through we want to do it in place, so we want to go through the number of rows. So here, say rows and columns, and these would be length of the board and length of the number of columns. And let's see if we have some constraint on the size here. So it's at least 1. Okay, good. So what we can do here is, so we have the board, so this would be our rows, and we can go through our columns, and we need the function to get the count of live neighbors, something like this, because that's what we use. So we can define this. And we get past the board, and we want to generate all the neighbors, valid neighbors, so both horizontal, vertical, and diagonal. So for an I and j in, so we'll have I plus 1 j, we will have I j plus 1, I j minus 1, I minus 1 j, and then the diagonal I plus 1, j plus 1, and then I minus 1, j minus 1. And what we want here is to do if this is valid, so we want to return those. So And then we want to check if the element there, which is board, that position, which is nij, is equal to 1, so live. Then we want to add it. So what do we care to add here? At the end, we want to just count. So what we want to actually is just count. So this is 0. And so here we should just add. And then at the end, we should return that. Okay. And now we could use that in our function here. So for board, and then we pass the index. And now we get to do our rules here, which are, so here we didn't change it, so we don't do anything. Here we didn't, here we changed it, so, and here we changed it. So here also one thing to notice is we changed it only, so let's first handle when it was live. So if board ij current, so we want to use current, right? So if this is equal, we want to pass current as well. So if this is equal to 1, then we do something else, we do something. So if it's live, then we want to change it here and here. So only if the count is less than 2, or so if the count is less than 2, or it's bigger than 3, then we want to change it, which means we want to set it to 0. So then 2 or bigger than 3, then we want to change it to be equal to 0. Otherwise, if the cell is 0, then only if it's equal to 3 we want to change it. And then we change it to 1. And these are the 2 rules that we have. We can also just make this simpler with this and that, and then here we can do end. And then at the end, so here we want to modify the board actually, but we want to pass the, so here we want to modify the board, but check the current value because we are doing things simultaneously. And so at the end we want to return board. Okay, let's run this. So we have a problem here. So we check this. Okay, so it looks like we have a wrong answer. So we pass current, we check current, and then we change board. And the rule is, let's go back and check our rules just to make sure we didn't. So any live cell with fewer than 2 live neighbors die. So with fewer than 2 live neighbors dies. Okay, we did that. Any live cell with 2 or 3 live neighbors lives. So we don't want to change that one. So we'll let it be. Any live cell with more than 3 live neighbors dies. So it's actually with more than 3 live neighbors, not with more or equal. And any dead cell with exactly 3 live neighbors lives, right? And so we set it to 1. Okay, let's see if this passes. still doesn't pass, so maybe we have something here. So we take the one on the below, the one to the right, the one to the left, and the one to the top, on the top, and then the one on the diagonal. So we want I minus 1, j minus 1, and then the other one is I plus 1, j minus 1. We don't have I plus 1, j minus 1. Yeah. So we are missing a couple of other ones. I plus 1, j minus 1. And then here it's j minus 1, I minus 1. We have that one. Here it's I plus 1, j plus 1. Here's I plus 1, j minus 1. Here it's I minus 1, j minus 1. And here it's I minus 1 and j plus 1. Do we have that? No. So I minus 1, j plus 1. So did I take all the diagonals, or is there a mistake somewhere here? Okay, so one thing that will make this maybe easier for me is to just do it with this method instead. And we'd have 0 minus 1, 1 0, minus 1 0, and then minus 1 minus 1, 1 1. So all permutations of 0 and 1. And then we would have minus 1 1, and then we'd have 1 minus 1. So overall 1 2 3 4 5 6 7 8, 3 here, and then another 3 is 6, and then 7 and 8. So we need 8. Yeah, I think that makes sense. And now we can just say for di dj in d, and ni and nj are going to be just I plus di and j plus dj. Yeah. And then now with that we'll check that I is within and j are within the, and I and nj are within the right things, right? And now we can just add plus 1 if it's equal to 1. Okay, so I think that should work. Okay, so it's still failing somehow. Okay, so let me just make this. So let's put first cell here and check the cell. So if cell is equal to 1 and life count is less than 2 and bigger than 3, then we wanna mark it as dead. Okay. Otherwise, if the cell is equal to 0 and life count is equal to 3, then we set it to 1. Okay. So we modify the board, and then here we only pass the board. So I think it should pass. Okay, maybe I'm doing something wrong here. So if cell is 1, and then we have that, and then if, what I'm going to do instead of this keeping current here, I'm just going to keep track of live and dead. Okay, and now here we can have, so this one dies, so dead, append I and J, and this one lives, so live dot append I and J. Okay. And then after that I can go through the board. So for IJ in die, I want to change the board and set this to 0. And then for IJ in live, I want to set it to 1. And then return board, just in case I'm doing anything that. So here it should be board. Should be also a smaller space than the previous solution. So it's dead actually here. Okay, so maybe I was overriding board somehow. Okay, if we submit this, okay, it looks like it passes. Cool. Yeah, so pretty much simulation. The main thing to remember here is to not override the board, and so that we can do it simultaneously. Basically, so that we don't modify a cell and change the state of another cell because we modified another one, right? Because they happen at the same time. The transition to the next state happens simultaneously. Yeah.